Welcome everyone. Today, we will present status for the exploration of intent management tools in 5G4Data, one of 5 use cases in the Intend project. We will provide some background for our interest in this topic, describe the 5G4Data use case, and discuss how the various Intend tools can act together to make network operations more efficient. Further, we will show a demo following the actions of the tools taken to fulfill the customer's needs, which are visualized in the dashboards of our 5G4Data observational twin. Finally, we will present plans for our next steps. Network complexity is escalating with the introduction of network slicing, multi-access edge computing, and heterogeneous hardware accelerators. Manual configuration of these elements is impractical and error-prone, especially when scaling thousands of dynamic workloads. Intent-driven autonomous networks address this by abstracting complexity and enabling closed-loop automation. We won't meet future scale and expectations with scripts and tickets. Intent-based operation is how we run autonomous networks that self-configure and self-optimize across the communication infrastructure. To ensure interoperability and industry alignment, the 5G4Data use case will explore work done by industry and standardization organizations. TM Forum, an industry organization, has for several years developed mechanisms for autonomous networks, including intent, ontology, provides a common language for defining intents, facilitating clarity and consistency. Intent, description, standardizes how intents are expressed and interpreted across systems. Intent, API, enables seamless integration with external platforms, supporting automation and extensibility. These mechanisms underpin a robust intent management framework, ensuring that customer needs are met efficiently, securely, and in line with industry best practices. This use case demonstrates natural language intents automatically driving network slice configuration and deploying the right workload to the right local data center as part of Telenor's future distributed AI factory scenario. At the heart of 5G4Data is a state-of-the-art infrastructure leveraging 5G advanced technology across 40 strategically distributed data centers, driving ultra-fast, low-latency connectivity. This network enables decentralized services, local processing, and dynamic resource allocation. The 5G advanced platform delivers the agility and reliability required for intent-based operations, supporting demanding customer scenarios and powering the next generation of digital services. We are building an integrated proof of concept with Intend tools and TM Forum mechanisms. Central to fulfilling customer intents are the Intend tools, validated across the 5G4Data use case. InChat captures and interprets customer requests. InServe maps intents to available services and resources. InNet manages network-level configuration and connectivity. InOrc handles workload deployments and monitors outcomes. The intent lifecycle traverses these components, transforming customer requests into actionable network operations. Validation confirms seamless integration, reliability, and scalability, ensuring every intent is accurately managed from input to fulfillment.
Before we describe the end-to-end proof of concept in detail, let us take a brief look at the intent observational twin we have created. When intents, their status, and intent observation reports are stored in a knowledge base as triplets, these triplets together form an observational twin of the system at the intent level. In the 5G4Data use case, all stored triplets follow the TM Forum intent ontology specification. As shown in the diagram on the left, all intent tools used in 5G4Data store intents and intent reports in InGraph. We also store infrastructure information as triplets in the knowledge graph. The Grafana dashboards that we will show shortly are generated from this stored data. Grafana, which we use as the dashboard builder, sends SPARQL queries to InGraph to retrieve the triplets that are then visualized in the different dashboards. For this introduction to the observational twin, we used synthetic data generated by an intent and intent report simulator that we designed and implemented in the project. This first dashboard examples gives an overview of all existing intents, along with some basic details for each one. We can also add more visual context. This dashboard overlays infrastructure and network intent information on a map. It shows the geographical location of Telenor edge data centers in Norway, Sweden, Finland, and Denmark. It also highlights areas where intents have resulted in the creation of 5G slice regions. A 5G slice is a virtual network built on top of the physical network designed to guarantee specific quality of service parameters. Dashboards can also be linked together, which allows for drill-down capabilities. From the map dashboard, we can navigate to more detailed views of a specific intent that resulted in a slice creation. This drill-down dashboard shows graphically observations of the quality of service parameters defined by the intent, such as latency and bandwidth guarantees. From the map view, it is also possible to select a specific data center and see all intents related to it. We can then drill down even further to view detailed metrics for each of those intents. Note that these are just a few examples. Many other types of dashboards can be created depending on the needs of the use case.
First, we will demonstrate how the InChat tool works and its usage in the Telenor 5G for data use case. InChat is the stakeholder facing conversational interface tool, part of the Intent Toolbox. It enables continuous natural language interaction between human users and the intent based management system. Through a simple chat interface, the user's requirements are captured, refined, and translated into a standardized TM forum intent format. The interaction starts when the user enters a natural language description of their business need into InChat. In this example, the user wants to experiment with local AI inference for a small business in Tromsø with strong privacy requirements and low predictable response times. InChat analyzes the input using a large language model running in the background. It identifies the intent to deploy a local AI application with strict latency constraints. Using information from InGraph, the intent knowledge graph, InChat proposes a suitable small language model and an appropriate edge deployment location that matches the user's requirements. The user reviews these suggestions and confirms that both the application type and deployment location are acceptable. At this point, InChat detects that some required intent parameters are still missing. It asks a follow up question to understand how the service will be accessed. The user replies that the application will be accessed from a mobile device. Based on this information, InChat determines that specific network guarantees are needed. It proposes suitable network parameters, such as bandwidth and latency targets optimized for mobile access and real time AI inference. The user confirms that the proposed network configuration meets their expectations. With all mandatory parameters collected and explicitly approved, the intent capture process in InChat is completed. Based on the acquired input through the dialogue with the user, InChat automatically generates a complete TM forum intent. This standardized intent is then handed over to InServe. Behind the scenes, each user input is processed using predefined intent analysis logic implemented as an action flow in InChat. The system continuously tracks missing parameters, consults the knowledge graph for recommendations, and guides the conversation until the understanding of the user's intent is complete. InChat then generates a TM forum intent that is passed to the follow up intent tools. This demonstrates how intent enables a smooth transition from natural language interaction to automated intent based service provisioning in the Telenor 5G for data use case.
So, InChat uses a large language model in addition to use case specific knowledge from InGraph. The use case specific knowledge in InGraph describes the infrastructure, the available workloads, and the geographical areas that could be used to configure geographical aware 5G slices. The use case specific knowledge is used to generate the formal intent specification in TM forum format. When the TM forum formatted intent is complete, it is sent to InServe in its turtle format representation. If the intent contains multiple expectations, in other words, both a deployment requirement and a network configuration requirement, InServe splits the intent into separate components. The deployment intent is sent to InOrch in the data center specified in the intent. Here, the application is deployed and monitored using the metrics defined in the knowledge graph. At the same time, the network intent is sent to InNet. InNet configures the required 5G slice using the geographical polygons and network topology to constrain the slice to the correct area. Since InServe is the handler of the intent, it will store the intent in InGraph when it is received. We can see that this happens in the live observational twin Grafana dashboard, and we can see in the InServe log that the intent was received and that it was split into one deployment intent and one network intent. The deployment intent is sent to InOrg running in data center EC21 since this was stated as part of the intent. The network intent is sent to the single instance of InNet. Note that the splitted intents will have new unique identifiers. This is important for the management of intents and their related status reports and metrics observations.
In this first phase, we show the containers currently running in our environment. These components constitute the infrastructure required to receive and process intents coming from InServe. The main architectural element is the InNet application, visible at the top. InNet represents the core of the system and acts as the intent lifecycle manager, coordinating the entire intent lifecycle, from reception and validation to enforcement and monitoring. We now observe the container logs during the startup phase in order to highlight their initial status. At the top, we find InNet. At the bottom left, we have the operation manager, responsible for executing operations toward the southbound domains. At the bottom right, we see the NSMF, the Network Slice Management Function, 3GPP plugin, which represents the entry point to the currently integrated southbound domain. At this point, we receive an intent from InServe. The reception of the intent triggers the internal execution flow and leads to the population of the knowledge graph. Through a dedicated service, we can observe the intent status, which already appears as provisioned, since the enforcement process is executed very rapidly. We can also see some of the network parameters requested by InServe, which have been correctly translated and stored inside the knowledge graph. By analyzing the logs, we can follow the sequence of operations and verify the correct execution of the workflow. Here we show in detail the intent received from InServe. The intent is expressed in turtle format and is immediately stored in the knowledge graph with an initial status of created. It then transitions to the validating state. This phase is not visible at this moment since provisioning has already been completed. During validation, the system verifies the syntactic and semantic correctness of the intent and then translates it into operational network configurations. The generated configurations are forwarded to the operation manager for enforcement on the network domains. The operation manager receives the request, interprets it, and processes it. Based on the target domain, it forwards the operations to the appropriate plugin, which in this scenario is the NSMF plugin. Operational checks are performed internally by the operation manager, which notifies InNet about the successful outcome of the process. InNet then proceeds with the subsequent phases of the intent lifecycle, namely fulfillment and assurance. The information is forwarded to the NSMF plugin, which receives all the translated and validated parameters, completing the enforcement on the southbound domain.
Each in-org instance is responsible for deployment, monitoring, and scaling of workloads in its respective data center. In-org consists of several components, and all the components run in a Kubernetes cluster. In-org uses the in-graph knowledge graphs to locate and download the Helm chart needed to deploy the workload as described in the intent. The in-org TMF proxy component implements the TM form 921 API, and when a deployment intent is sent from InServe, the proxy will parse and analyze the intent. The deployment intent includes a link to the where in the workload catalog the Helm chart is located. The deployment Helm chart is downloaded using this link, and the deployment is then done to a separate namespace in the cluster. The cluster then downloads the associated workload container or containers from the GitHub container registry, since this is the container registry we have used to store workload containers for the 5G4Data use case. The proxy transforms the TM form intent into an Intel intent-driven orchestrator compliant intent, and the resulting compliant intent is handed over. The orchestrator informs the planner about the new workload, and a scheduler for the workload is created. The workloads will store its KPI metrics in its accompanying Prometheus component, and the planner and scheduler can observe the metrics and make scaling adjustment to keep the workload within its intended performance requirements. Throughout this process, although not shown in this animation, all intents, state changes, and observations are stored in the intents knowledge graph. This allows the system to track whether intents are fulfilled and to react automatically if performance targets are not met. In this way, natural language input is transformed into coordinated actions across compute, network, and geography, enabling automated, intent-driven 5G service provisioning and workload deployments to local data centers for the serving area.
In conclusion, the in-graph, in-chat, in-serve, in-org, and in-net tools demonstrate a robust end-to-end flow, from intent capture to service fulfillment, validated through the 5G4Data observational twin and accompanying demo scenarios. This marks a first step toward fully autonomous, intent-based networks capable of self-management and large-scale operational efficiency. The results from this validation will contribute directly to Telenor's strategic roadmap toward autonomous operations and strengthen ongoing engagement with industry ecosystems driving automation and open standards. This has been the first step in the integration and validation of tools in the 5G4Data use case. In the next steps, we will involve 3 additional tools, namely InSustain, InExplain, and InCord. All of these are non-functional tools which rely on observability of intents and intent reports. Further, InCord will suggest changes if needed.
More information about the use case and the tools are available. A detailed description of 5G4Data in Deliverable D 1.2, use case definition and MVS. An interactive tutorial of 5G4Data focusing on, among other things, intent preparation, creation, and communication. The Intent project code repository and the official Intent project website are all great starting points for more detailed information. Thank you for viewing this video.